This is an interferometric setup that I used in a previous video to study the sideband noise in Schottky diode frequency doublers. So this is one doubler, a hybrid and a Schottky mixer. And this is another identical doubler. And they are sitting in an interferometer, means there is a common oscillator, and then the signal is split. One goes this way, another goes that way. And look at the previous video for more details. The problem with this is that the result is unexpected. It's not so easily visible here because it has the normal flicker noise at a fairly high level, but it has a noise hump at about 120 kilohertz or so. And the purpose of this video is to try to find out what is the reason for that. Here is what it looks like. And it's quite clear that the noise goes down and then it goes up. Now it's only 2 decibels per division, so it doesn't look so dramatic here. But certainly this is unexpected. I have now modified the interferometer in the way that the hybrid here at the output of the interferometer, where the difference and the sum of the 2 signals coming in go here and here. The difference should be only noise, and I have changed nothing in this path. But the sum, which was previously only used to look at on the oscilloscope, now I am routing the sum signal into a stepped attenuator followed by a 20 dB coupler, where I can look at it with the oscilloscope, and then a selective load at 20 megahertz. Means it loads at 20 megahertz with 50 ohms. And then a quarter wave cable followed by a notch. This notch is a short circuit on 20 megahertz. So a quarter wave away from it, the impedance is very high, which means that this signal is looking into a 50 ohm load and nothing else. But at an offset frequency, this selective load, it has a very high impedance, so the signal just travels through, and the notch has a very high impedance also at an offset frequency. So an offset signal goes straight through, but a signal on 20 megahertz, after this notch is another 20 quarter wave cable, which inverts the impedance for the next notch to become very efficient. And then there is another notch, and then one more notch, all separated by quarter wave cables. After the notches, there is a band pass filter at 20 megahertz, because there is a signal at 40 megahertz and also some at 10 megahertz and a little bit less, but a signal also on 30 megahertz. And of course, this selective load and the notches, they don't affect any other frequency than 20 megahertz. Then low noise amplifiers, 2 of them, followed by the SDR-IP. The SDR-IP was previously sitting here, but now I have an ephedry net ephedry, I don't remember what it's called more, where I can check the ratio between the carrier and an injected signal that I send in here in one coupler, and then I have this other coupler to detect what is passing through here. And you will get a better understanding from the previous video where I do this measurement. Here is again the difference signal with the noise hump at something like 19.89 megahertz. And here is the sum signal. And it has a peak here. 19.89, maybe 87. I didn't do that so carefully. Anyway, the noise generated in the two multipliers has to be uncorrelated, and therefore the sum and the difference between the noise signals should be the same. So I will now evaluate what is the sideband noise level here in the sum signal and here in the difference signal. And if you look here, the curve looks a little bit more complex than it does here. But this is the Perseus, and I have not calibrated it. So I insert the stepped attenuator for a lot of attenuation. And here you can see it's the properties of the uncalibrated Perseus. So this will disappear when I do proper calibrated measurements. I am calibrating on the Netafedri. So I have clicked on the carrier at 20 megahertz and set the level by calibrating it here, so it shows 0. And then I have injected a signal at 19.89, and it's here. And I move it into the filter, and I have set this signal to be 80 decibels lower. 80.0. And then I go for the SDR-IP, the sum signal, and I have this injected signal here, and I have to calibrate it to make it show minus 80. Like this, now minus 80, and I switch off that signal. And here is the noise floor in a bandwidth of 1 kilohertz, and it's minus 143.1. Then I switch it on again, this generator, and do the same for the Perseus. That is the difference signal. I have to change calibration here. So now it shows minus 80 also on the difference signal, and I switch off here and look at the noise floor. (143.18 minus), and I had minus 143.16 here. So it is very similar. I will switch in the attenuators. Those are here. To see where the system noise floor is. And it's a bit below, but not very much. I had 143.2 about, and now 147. That's about 4 dB. And here I had the same, 143 point something, and it is minus 149.2. So the noise figure is probably a little bit better here. I say probably because I have not these impedance matching things in. And you can see here the effect of the notch. That's a bit surprising. No, of course not. That's because the impedance is very different on the notch. But here at 110 kilohertz below, it is close to 50 ohms. But I cannot be sure it is exactly 50 ohms. I now disconnect one of the frequency doublers by moving a cable, and then of course the different signal becomes huge. It saturates something, but the sum signal that should go down, I expect, by 3 decibels from here to here. That is roughly as expected. But I can still see this noise peak. I don't know the reason for all these equi-spaced spurs. Maybe because of something saturating. Anyway, I will put that frequency doubler back and disconnect the other one. Here the noise is stronger. Minus 145 rather than minus 146. If I remember right, I think it looks a little bit different also. But I don't know how to interpret this. It seems to me that the noise actually comes from the frequency doubler and it's not generated by the oscillator. The oscillator is much purer than what we guess from this. But it is a frequency doubler and I don't know what peculiar effects may be present here. This is what the entire setup looks like. So the interferometer is as before, and here are the selective load and notches and quarter wave cables and a filter and low noise amplifiers. There is an attenuator between them to not get too much gain. I have now eliminated the interferometer, means I have taken this signal directly into the hybrid, and then the output here directly into this way, so it goes into the stepped attenuator. No, sorry. It goes directly into the selective load here. So I skipped the attenuator and the coupler because I don't need the oscilloscope anymore. So now it's just a notch filter setup. And here is what it looks like. I have the calibration signal running and I switch it off. And here comes the noise floor. Minus 146.9. I have now connected the other Schottky mixer from the other frequency doubler, and I think the shape is a little bit different. Calibration did not change, and I switch off this generator, and now the noise is minus 147.6, so it is different. Well, what conclusion to draw from that, I don't know. The Schottky mixers have ferrites inside, And I have put a strong magnet here on top of the box, trying to find the sweet point. Signal level did not change. It's still minus 80, and I haven't changed calibration or anything else. And I switch off the signal generator and look for the noise floor. And now it's minus 148.8. And I think that's a little bit better than before. And now I will look for an ugly point. Seems the iron is a little bit saturated because I lost half a dB in the signal level. But there is a lot of noise. It's minus 138. That's 10 decibels more. And that peak that was so clear before is not so obvious anymore. So it seems the problem with the Schottky mixers as frequency doublers has to do something with the iron, and probably not with the diodes, but there could be diodes also, of course. This is an experimental high-level mixer. It is not so good at close-range sideband noise from interferometric measurements, but as a frequency doubler it behaves very differently from the mini-circuits mixers. The level is a little bit higher, so I see occasional problems from the crystals in the first notch filter, because the power is a little bit too high for that. But that problem does not extend to 100 kilohertz below the carrier. So I calibrated again to minus 80, and I have verified with the net ephedry that the signal is 80 decibels below the carrier. And switch off the signal generator and look, where is the sideband noise? Minus 151.9. And there is not this ugly close range peak. I do see something at a large frequency separation here. I don't know if this is sideband noise from the mixer or if it is something else from the system. There are selective components, filters and other stuff here. This is what the experimental mixer looks like inside. There are many Schottky diodes. I think maybe you can see it. So they are connected in series in groups of 1, 2, 3, 4, 5. No, 1, 2, 3, 4. 4 diodes in series, and then the configuration is a high-level mixer configuration. We'll see if I have some description about it somewhere. And there is some resistor and capacitor to cancel the coupling between LO and RF, because this is not the proper wideband design. The ferrites are fairly large, so probably they are okay at this power level. This is the schematic diagram, but these two are on the same ferrite core, and these two are on the other ferrite core. So RF, IF, and LO. The noise hump obviously comes from the Schottky diode mixers. Now this is at a fairly high signal level, it is plus 27 dBm into each frequency doubler. And at that signal level, there is some compression. It's 2 dB less than the level I have at, let's say, minus 21, that's here, where the loss is 10 dB, and here it is 12 dB. So going down to minus 21 dBm input power, the output power is going to be about plus 11 dBm. And that means if the amplifier following after would be 1 dB noise figure, it would be 173 plus 11 means 184. That would be the here somewhere, the flat noise floor. Now in the setup I have, there is some noise sources and other stuff, so I don't see quite as good. Anyway, to get a better performance, I think one should use an active frequency doubler. This is the experimental mixer. It has a maximum here that's 1 megahertz below the carrier. And if I look on the other side, means I change the frequency by 1 megahertz. Then the carrier is here, and the maximum is about 600 kilohertz up, but there is this sharp feature at 1 megahertz. So when doing this properly, means calibrating with the reference signal on each frequency, I find the following. Differences are not very big, but it's more than 1 dB at 1 megahertz. Strongest is the signal on the negative side, but on the positive side, the signal at half a megahertz is larger than the one at minus half a megahertz. So there is definitely an asymmetry here. Means that the noise has to be AM noise plus FM noise, and they have to have a correlation. Means the phase angle between them cannot be exactly 90 degrees, as I have seen in other devices. Well, I don't find these kind of mixers very interesting anymore. I will look at other architectures.